science and collaboration in EIC shines through advising and maintaining a group of exceptional postdoc fellows, graduate students. He organizes international workshop on the science of EIC, seminar series, and visitors program and annual summer school. These are all on EIC. Of course, he is a recipient of many awards, very prestigious awards. Some of them I just would like to mention here. One is a SUNY Chancellor's Award for Excellence in Research and Innovation in 2018. Riken President's Special Prize for the Study of Nucleon Spin in 2015. He is, of course, the Fellow of the American Physical Society since 2014. National Academy of Science and Education Fellow in Life Sciences in 2013. And very recently, he has been awarded as a special eminent alumni of IIT Kanpur, along with many prestigious people. As I said already, that I know Professor Deshpande since long, since our days in Brookhaven, when we started joining STAR that time. And today I am very happy that at this 6 o'clock or 6:30 in the morning, cold time, he has agreed to talk on Electron-Ion Collider, physics opportunities and experimental challenges. So thank you, Abhay, and please go ahead with your presentation.
Thank you, Subhashis, for this very kind and very august introduction. I'm going to talk to students, and I'm hoping that that introduction doesn't intimidate anyone. I do want to have questions and a conversation with the students here. So let me share this screen. You should be seeing the whole screen now. And yes, I hope that you can hear me clearly.
Yes, it's perfect. Go ahead.
Okay, very good. So I never refuse an opportunity to talk to students, no matter where they are. So I'm pretty used to getting up very early, because just last week I was talking to students in South Korea, which was even earlier than that. So you let me sleep a little bit more. So thank you very much. It's a pleasure to talk to you. Some of the things that I'm going to tell you are probably going to be familiar, because this audience is already involved quite deeply and very impressively. Some of the students and postdocs part of the Electron-Ion Collider activity have made very significant contributions already over the last 1 year to the project. So I'm delighted to have them, some of them in the audience, and we are very graciously happy to see that India is growing its influence in the Electron-Ion Collider. For those who are not in the part of the science and not been thinking about the Electron-Ion Collider, I have a broad introduction in this talk to the science of Electron-Ion Collider. It will be non-technical. I apologize if it comes across as too rudimentary, but the aim of this talk is to give you the concepts and the background and the history of why Electron-Ion Collider became the project it is. I call it, in tongue-in-cheek, to call it a new collider to study a super God particle. And I will explain to you why I call the super God particle to what I'm going to talk about. It is probably, you have guessed, Electron-Ion Collider is about the gluons. In the past, I have given talks that have titles like to study the glue that binds us all. That is the motto of the Electron-Ion Collider, the glue that binds us all. So it gives you a hint that I'm going to call the gluon the super God particle, and there is a history to that, and I will talk about that as I got through. So why? 1 minute. It's a major step that has happened over the last couple of years. In 2020, after about 20 years of our effort, Department of Energy in the US announced that the Electron-Ion Collider got a CD0, which means that the project will be built in the United States. That's the technical interpretation of it. And not only that, they announced that the site of the Electron-Ion Collider will be Brookhaven National Laboratory. They also emphasized that the collider will be built by BNL and Jefferson Lab as partners together. Those were the two competing groups that were coming in to build the collider. And now they have said, the deciding committee said that we should join forces and realize the project as a joint project. I'm very happy to tell you that the next step in the approval process, critical decision 1, CD1, which is a very important milestone to have a start engineering designs of the project, was also given to us early this year or mid in this year, June in this year. If the project remains on the timeline that we envision, then I can tell you that the first collisions, what we call CD4A, will happen sometime in the late FY 2029, and the physics start will start around 2032, so about 10 years from now. Some of you might say, if it is 10 years from now, why are we worrying about now? Well, when you build a new collider, you build new detectors, it takes this kind of a timeline to realize this. To conceptualize it, it took us 20 years. To formulate the science, to defend the case. And now we are in the final phase of realization. So we are all excited. And 10 years from now, many of you in the audience, and particularly I'm looking at students and postdocs, will be in the driving positions in faculty at universities and national labs in India and across the world. And I think this is a project, if you're interested in QCD, it is a project that is so unique, and I will try to tell you why it is unique and how it is unique. It is so unique that the science will not be done in any other place before that. So that uniqueness assures me that many of you will be in leading positions in the science when the science actually comes out. Some of us who have proposed it for many years and helped realize it will be fairly old by that time. So I'm looking really at the students and the postdocs at going forward with it. So the quest for fundamental structure of matter is not new at all. All of us at some point in our life have wondered, what is the smallest thing in the universe? What do we think about? How is it made? Where is it come from? What is fundamental? How do you define it? And National Academy of Sciences had this report on the Electron-Ion Collider. They opened their section with this kind of a diagram that most of you in the audience know, that the matter is made up of molecules, that the molecules are made up of atoms. At the center of it is the nucleus, which has the protons and neutrons. The nucleus is made up of protons and neutrons, and those two are made up of quarks, and they are bound together by gluons. So this is something that we all know now probably in the junior college or undergraduate college. You learn about atomic structure and the state of the art of the Standard Model. But how do we know this? Well, let me give you an example, and I'm going to try to convey to you what resolution means to us. So here is a picture of something, and I'm now a resident of New York, so some of you can guess, I'm giving you a hint, what this might be. What I want to emphasize is the concept of resolution. Resolution means that in this picture, I have this size, which is about a quarter of a half a centimeter square, is the smallest element of this picture, and that is my resolution. And with this resolution, you cannot, or maybe some people can judge it already, guess what it is, but you cannot guess what this object is. For that, I need to increase the resolution. So I have to increase the resolution by factor 2. And maybe some of you have started thinking about, oh, what might this be? But it's still not clear what it is. And now you might start thinking, okay, I think I can see something. I mean, now I'm at a third of the resolution or 3 times the resolution that I started with. And I am from New York. I've given you the hint. And I think you can probably guess that this is Statue of Liberty. This is the Statue of Liberty. What I did was I looked at the Statue of Liberty with higher and higher precision, higher and higher resolution of my probe. And probe here means my light probe. And that's how you see the smallest things. But those who recognized what this was at this stage or at this stage, you had in their mind some ideas already as to what this might be. I had given you a hint that I'm from New York, and Most people know that this Statue of Liberty is somewhere in New York. So I think if you have some mental picture, some bias in your mind, you can recognize this very quickly. What we did in this place is that we started to look at the lambda, the wavelength lambda with which you were scattering off of the Statue of Liberty became smaller and smaller. And at some point, the Statue of Liberty came very clear. To do that, what we had to do was to go to higher and higher momentum of our probe. And this is something that you probably remember from undergraduate physics. Typically, the momentum of the probe is inversely proportional to the resolution of your instrument. So why do we need high resolution? So here is a simple picture. You've seen the microscope. We have a resolution. We've used light wavelength, about 380 to 740 nanometers. That gives us a resolution in a simple microscope of about 200 nanometers. If you use an electron microscope, the wavelength drops to 0.002 nanometers using about 100 keV electrons. Using that initial formula, the resolution drops down to about 0.2 nanometers, about 1,000 times better than that. In particle physics or in nuclear physics, what we do is that we increase the electron energy even further, not 100 keV, but about 20 GeV. 20 GeV allows us to look at wavelengths which are of the order of 0.01 femtometers. And suddenly your resolution now starts becoming of the order of 0.1 femtometer. And that's what a particle physicist in fixed target experiments have done. You have done electron beams coming from an electron accelerator and hits a target. And then we build a detector as experimental physicists to look at what comes out. And we collaborate with our theoretical physics friends who then look at the data. And once we produce the final observables, they, along with the experimentals together, form the idea as to what the picture might be at the target to result in a scattering process that we see in the detector. So that's the whole scientific process, and that's the way we have discovered most of the standard model that we know today. And the critical thing is to go to higher and higher resolution. What do we know now? So let me jump to our state of mind. We know that we are all made up of molecules, which are made up of atoms, and those are made up of nuclei at the center, and nucleus carries most of the weight of the atom. And then the nuclei are built by protons and neutrons, and they are made up of quarks. There are 6 types of quarks, each with 3 different colors, and all of this you probably know. I want to emphasize only one thing in this slide. That thing is here. The electromagnetic interaction that happens at the atomic level, at the scale of a few nanometers, that is mediated by photons. Photons do not carry any charge. They're not positive, negative in the electromagnetic sense. They don't have any charge. And field theory tells us if there is no charge, then you cannot interact with each other. So the photons cannot interact with each other directly as one would expect photon interacting with a charged particle like a positron or a proton. There is an interaction. It can radiate a photon only if you have an accelerated charged particle. However, there is a difference is that inside the proton or a neutron, the gluons that interact between these quarks, they themselves are charged. So like the quarks, which have 3 colors, of course, the gluons have 3 colors. And now you have a self-interaction possibility. That self-interaction means that they can interact with each other. That means that the photon can split into a gluon can split into 2 gluons. Those 2 can split into further gluons, etc., etc. A process that normally is impossible when you think about an electromagnetic interaction. And that is my cartoon of distinguishing between QCD from QED, quantum electrodynamics from quantum chromodynamics. What you can see is that this is a gluon. It can split into quark-antiquark pairs, or it can also interact because it has color. It can have these 3 gluon vertices or 4 gluon vertex. These are possible only in QCD. If you go to QED, a photon can actually split into electron-positron pair or quark-antiquark pair because quarks carry electric charge, but you can never have a photon splitting like this into 2 photons in a direct way. And neither can you have this as a direct way. So this is the big difference. And this part, these self-interactions inside the proton are the one critical thing that distinguishes electromagnetism from quantum chromodynamics and creates all the richness, all the intriguing and puzzles of QCD that we study in many different ways. We study it with using proton-proton collisions. We study it using nucleus-nucleus collisions, proton-nucleus collisions. And I'm trying to tell you that the electron-proton and electron-nucleus collisions are also being used to cleanly explore what's going on inside the proton or in nuclei by using an electron probe. So such methods have been used in the past, and now we know the standard model. I don't think I need to introduce this to this audience, but I want to focus on these 6 types of quarks and this type of gluon that we are going to be focusing on. The electroweak part and their exchange bosons are given here, and the neutrinos and the leptons are on the left side here. I want to focus on this part one, the Higgs boson, which has been called the God particle because it does give mass to most of the particles that are shown in this left-hand side, particularly the quarks. So it does give mass to the quarks. The gluons and the photons are massless, so that's not useful. W's and Z's get huge masses by interaction or interactions with the God particle. Now, I'm going to claim that the gluon is a super God particle. Super God particle. The reason is that the proton mass puzzle is you probably know, in 2013, after the discovery at CERN of the Higgs boson, in 2013, these 2 gentlemen got the Nobel Prize for the Higgs boson because they understood how mass is created in the universe, which is absolutely wonderful. Now the problem is the proton mass puzzle is that if you take the 3 quarks which form the proton and you take their bare mass, it comes to about 2 times 10 to the minus 26 grams. But the proton, which is made up of those 3 quarks and lots of gluons and maybe C quarks that come from those gluons, their mass, that mass is about 200 times, 300 times more. It's about 16 or 168 times to 10 to the minus 26 grams. So where is this mass coming from? The gluons, I've told you, are massless, and 3 quarks do carry only very small amount, fraction of the proton's mass. So where is this factor of 100 come from? And that we now understand. It's like saying 1 plus 1 plus 1 is about 300. That's not true, but it is true when you enter the world of QCD. If there are lots and lots of gluons, most of the quark mass is becoming from the Higgs mechanism, but that's 1% of the mass. The rest of the mass that you see inside this proton comes from gluon interactions, the energy of the gluon interaction. Although they are massless by themselves, the energy carried by them by equal to MC squared rule gives 97% of the total mass of the proton. And that's why I like to call it, to remember this very distinct difference between QED and QCD and what effects it does have and what it could be meaning towards a quantum field theory is something that I'm fascinated by. And this is why I call it in such talks a super God particle. 99% of the mass of the proton coming from a 0 mass particle or 0 mass vector boson or their interactions. And imagine this extends everywhere. Protons and neutrons are the bulk of the atomic mass. Atoms basically form all the elements in the universe. So everything that you see in the universe, the entire universe, the mass of the entire universe is coming from these mass 0 gluons. Imagine that, the entire thing, all the galaxies, everything that we see, the mass of it comes from this interaction, the gluonic interaction. And that is a fascinating thing to think about. So you should think about it in your mind. So it has very significant consequences as well. And this is the mischievous part of this gluon. On the left-hand side, we have the atomic structure. We understand atomic structure so well now that we define time using electronic transitions of CCM atoms. The current best clock in the world, which sits in Colorado, it measures with the accuracy of 1 second in 220 million years. That's the accuracy with which we can now determine time, or in fact, define time using that electronic transition, because you understand the atomic transition so well, electroweak force so well, so precisely. Now, if you were trying to do the same thing with the proton, then the internal structure is not known to better than 20 to 30%, which means that to compare to 1 second in 220 million years, you would get an accuracy of 20 minutes in an hour. That's the time resolution that you can get if you actually time your time like clock using understanding of the gluons or the internal structure of the proton. So this is something that is very interesting, that both the atom and the proton were discovered about 100 years ago, but we know so much more about the atom and so little about the proton. To overcome that, to get to something like 1% or better, I would like to propose that we need to look at the proton again using deep inelastic scattering techniques. Deep inelastic scattering means that you're going to use a probe that goes inside the proton. That's the deep. Inside the proton means that I'm going to break the proton to some extent and look at inside with high resolution. Feynman said that scattering protons on protons to look and understand what the structure is like colliding two Swiss watches to find out how they are built. I claim that you cannot really understand how they are built. All you can do with the violent collisions of two Swiss watches is that you know what was in there, because you'll break them and everything will be scattered. It might be very difficult to put it back together. So I claim that you will not understand how it is made, but what it is made up of. But the question is how it is made. And I want to give you a different analogy. If I wanted to understand the structure of the watermelon, I can do an experiment as we do at RIC or LHC. You collide very high energy watermelons on each other, and they break and they fall like that, and you know what's in there. You know, there is meat, there are seeds, and there is this border, there's a shell of white, etc., etc. But if I ask you, tell me what is the precise distribution of seeds inside the watermelon, this is not the right experiment to do. The experiment to do is to collide the watermelon with a very sharp knife. And this is what this person is doing. He's cutting the watermelon with a sharp knife as he likes to see the distribution. And then by cutting it as you want, you can actually see the distribution of seeds in a way you can control. And this is the difference between what the electron-ion collider will do with the ion compared to what many of you are doing at ALICE in the nucleus-nucleus collision, or proton-nucleus or proton-proton collision. Now, proton-nucleus collisions or deuteron-nucleus collisions that you might be doing at RIC or at ALICE comes very close to the electron-nucleus collision I'm showing here on the right side. However, it is still much more complicated than an electron-ion collider, because electron itself has no QCD inside it. It's a point particle. It is purely electroweak physics. So we are using the power of electroweak physics, the precision that allows us to make the clock sensitive to 1 second in 220 million years. That type of accuracy, which the electromagnetic interaction brings to power, that's what we want to use. When you collide proton or deuteron on the nucleus, you don't have it, because the probe itself has large uncertainties, because those are quarks exploring the inside of the nucleus on the other side, quarks inside a proton looking at the nucleus on the other side. So there is a significant reduction in the cleanliness with which you can measure things with the electron. And that is mainly the reason why most of the standard model of physics that I described to you before, it started the discoveries with the electron or muon scattering. So there is a history to that as to why we want to do it. Now, this is how we would do it. The electron comes through, exchanges a virtual photon with a wavelength which is smaller than the size of the proton, and then the proton gets split. There is a remnant jet that remains, and the current jet comes out, and Professor Deshpande looks at it from this side, and from this side, and from that side. So these are my eyes looking at it, and that's what we want to do. The lambda is, I remind you, h by q squared. The smaller the q squared, the larger the lambda. Larger the q squared, the smaller the lambda. And that's what we want to do. To go inside, we want to make sure that we are inside the proton. We call it deep inelastic. The knife remains the same, and the watermelon is cut as you want it. Now, a more technical introduction to this is that this is the same diagram. It's the photon being exchanged. The beauty of this is that this q squared, the momentum exchanged between the electron and the nucleus, is given as q squared. The four momentum squared is the measure of the resolution, as I told you before. It's simply the difference between the incoming momentum and the outgoing momentum of the electron. That's just very straightforward to understand. Now, the inelasticity, how badly you break the proton, is given by this 4 vector, which actually, if you look at it, turns out that it actually depends reduces to the same 2 things that we measured in the previous case: the incoming energy of the electron, the scattered energy of the electron, and the scattering angle. And this also can be reduced there. And then the variable, or the favorite variable of deep inelastic scatters, the X Bjorkane, which measures the momentum fraction of the struck quark inside the proton, is q squared by sy, where s is simply the square of the center of mass energy. All of these then depend on these 2 things: the incoming energy, the outgoing energy, and the scattering angle. That is the beauty of this measurement. You only need to make extremely precise scattered electron and scattered hadron, scattered angle, and you can get the first estimate of the interactions that happened on an event by event basis inside in the collision. Of course, you can do much better by tagging all the hadronic debris and the jets that will come out, and I'll come to that a little later. But my basic idea is that you can do this very, very precisely. Now, based on such measurements, you can have 3 types of measurements. One is called the inclusive measurement, where you only measure the scattered electron. If you become more ambitious and start measuring what is coming out of on the jet side, then you become semi-inclusive. And exclusive measurements means that you measure everything that happens to the nucleus when you hit it. And that's what the electron-ion collider looks like. We are going to scatter electron using such a counterclockwise electrons and nuclei, and we're going to measure everything we can in this process. Now, let me briefly give you a high-level overview of the physics of the EIC. However, I want to show you something. Why is it relevant, and where is it relevant? You all are familiar with this figure, and many of you are part of this figure in the sense that, well, not just here today, but on this side in the investigations at the LHC protons, maybe the LHC heavy ions. The ALICE experiment sits somewhere in this time frame after the evolution of the universe, and this is the time where the formation of nuclei begins. The formation of protons have already occurred, and the formation of nucleus begins. So when you tune the RIC or LHC to an energy, you are at one point in this diagram. You're at one disk, and you need to change the energy a little bit to go around it. But there is a small variation in the energy that is allowed by hadron collisions, and that allows you to study something. What Electron-Ion Collider does is, because you can study the electron scattering at different angles and different energies, you can tune your energy, your probe of Q squared over a very, very wide range with high precision. And that high precision and wide range allows you to start studying how the protons are being formed, which is the beginning of the hadronic transitions, fragmentation, quarks and gluons becoming hadrons of different kinds, and then light nuclei being formed and the heavy nuclei being formed. All of it can be encompassed. So what you're trying to do is, with high precision, go over a very wide range of swath in timeline of the evolution of the universe, all the way in. I would agree. I would argue to some extent you can do exclusive measurements, which you don't even break the proton, which means that you're measuring things at a very, very late time scales. So the physics that I've sort of given you a very overbrushed view was divided into 3 major thrusts. One was, and I'm going to tell you about them. One is, what is the structure of proper protons and neutrons in terms of their quark and gluon positions and spins? You know, all of them have spin, and we don't quite today understand what the proton spin is about. I mean, we did a major discovery at RIC using star and phoenix detectors using polarized beams. We have figured out that the gluons are non-zero, contribute to the proton spin. We had studied in my earlier experiment at CERN at NA47, which was called the spin-muon collaboration, or EMC, that the quarks carry a small amount of spin. But now we want to understand really where is the remaining spin coming from. 50% of the nucleon spin is still not understood. So how do nucleon properties emerge from the quark-gluon interactions? This is something that we would like to see. The second pillar of the science is of using nuclei. If I hit with my deep inelastic scattering photon a quark inside a proton inside a nucleus, how does this color interaction happen? What are the interactions that happen inside the nucleus? And how does the transition happen at the border? Or does it happen at a border of a colorless meson that comes out? We always see only colorless mesons in the world. We never see colored particles. So how is this transition happening, starting from a colored object passing through? What are the interactions? This is very important because this is deeply connected to fragmentation functions, and fragmentation functions, a quark going into a pion or a kaon, is extremely, it's a non-perturbative offer effect, which really needs to be understood very well. And it is deeply connected to the ultimate question in QCD of confinement. Why is color confined? And I think this is a fascinating field that we would like to measure. We can measure things with the nucleus here, with very large variation nuclei. We can put a detector here with appropriate particle identification. You can look at light versus heavy quarks, etc., in a real laboratory setting, which has never been possible in the past. And last but not the least, I told you that the gluons have this property of color. They can split into each other, and more gluons can be formed. It is predicted that at high energy, that means when you're looking at extremely low values of X bjorkane, the gluon density in the proton or a nucleus becomes extremely high. It comes out very naturally in the theory itself by processes that gluons keeps on splitting like this. But we also have seen that in Hera, in an experiment that we did about 20 years ago. We discovered that the gluon distribution keeps on rising, and I'll show you a little bit later what that plot looks like. And we don't understand where it will saturate. We don't know where it saturates. The QCD by itself does not tell us, but it does tell us that there is another competing mechanism of gluon recombination that should start inside all protons and nuclei at high energy at some point. And then these two becoming equal will make it saturate. And that's the idea. That's the discovery that we want to see, because that kind of medium that is created when gluons saturate has extremely interesting properties. And if it is true, for example, it has like 100 times the energy density of neutron star. If that is the case, you should be able to see beautiful diffractive patterns using deep inelastic scattering. It's like a gluon wall, they call it. And does it really happen? Is the QCD as we know it really correct in the way we think about it? This is the kind of thing that we want to measure very precisely. So those are the three things that we promoted as the major thrusts of the electron-ion collider science. Let me give you a brief. How am I doing on time? Halfway there. Good. So the first thing I wanted to explain to you is this is the spin half of a proton, which comes from contributions from the quarks, delta sigma, which is the spin orientation, and LQ is the angular momentum of quark inside the proton. And delta G, which we have measured at RIC recently, which is the angular pointing of the gluon distribution, and LG means the orbital motion of the gluons inside the proton. If you make a spin structure function in which you see the difference between the cross-section of electron scattering of a proton, a polarized electron, when the proton is pointing this way, versus the when it is that way, that G1 structure function gives you precise information about this delta sigma, the quark contribution. And if you make this measurement over a wide range in Q squared, the resolution scale, then you start getting very precise information about the delta gluon, the delta G. And that's what we have done in the past. We know exactly how to do this. And we will do a beautiful experiment at the EIC by measuring the spin structure function of the G1, extremely understood, very precise measurement. And what you will get is that G1 spin structure function, which currently is very precisely known in the high X part because of the fixed target experiments at CERN and at SLAC and at Jefferson Lab. But as soon as it comes to 10 to the minus 2 or so, a few 10 to the minus 3, the uncertainties start growing, and all of these curves are consistent with the best global fits that you can do here. The Electron-Ion Collider will start making very precise measurements in this area, which is current prediction here, this diving of the G1 spin structure function. If we can see it, it will be great. And the higher the center of mass energy, the lower you will go to this X and make these beautiful measurements. The consequence of that is shown on this side. It says what is the total gluon and quark contribution to the nucleon spin in the region higher than 10 to the minus 3, which is plotted on the x-axis, and the one coming from the lower side, which is the 10 to the minus 6 to 10 to the minus 3. So from all the way down here, see the contribution is going to be small because it's x times the area under that curve that really matters. So the contribution is going to be small, but the uncertainties are very large. And this is what we will do at slowest energy at about 44 GeV center of mass of a collider experiment. You can do this, but as you increase the center of mass energy to the maximum that we will plan to do in the EIC, and this is what we wrote in the proposal, that we will be able to make a very, very precise measurement of the gluon distribution and the quark distribution in this possible way. What that allows us to do is to make very precise Parton distribution function measurements. This is the gluon distribution. As you can see, this is what we have uncertainties. After the RIC program, these kind of uncertainties that you can probably see this light blue color existed even here. So the curves would go before RIC program, it would go here like this. And that has brought us down, the RIC has brought this down to about this area, but RIC runs out of energy to do this very precisely below about 510 to the minus 2. And then EIC will take over and push this boundary to about 10 to the minus 4 or so. And I think you can see that it will be a huge improvement in the gluon distribution function. Similarly for quark distribution, but the quarks live in the valence part region, so we already know very precisely what they are doing in this region. We will get better understanding of this in the low X region. But their contribution there is rather small compared to the gluon uncertainty that is coming here. And then that can translate into the anti-quark distributions that we also do at RIC, the delta U bar, the delta D bar, and delta S bar. And all of them, you'll see a very significant improvement in the knowledge of these Parton distribution functions. Now, in a future experiment, you don't want to figure out only what's going on in the linear dimension. We are talking about only X dimension, the X Bjorkane. I would like to really see the proton in 3 dimensions. So although I understand this is a human being, I also know that the real picture is right here. And I want to see the same thing happen to the proton. This is an approximation of a proton. This might be the real photon, which means that I want to see the proton in its 3 dimensions. Now, I can't see it as a 3 dimension because I can't scatter anything off of that size and look at through my eye. However, I can do an indirect experiment. I will try to look at the proton as it comes to me. So here is a proton that is coming to you, and look at it as a transverse dimension. And there are different ideas, and different people have promoted different theories based on the energy at which we explore the proton. And the first one is the MIT bag model, where the quarks are inside a confining bag of gluonic attraction. If you look at that with a high resolution, because of the resolution, the probe is now looking at smaller bits, it will look something like that. And if it has a dimension, and we know that proton has a dimension, but how we don't know quite understand what the distribution of the color and the electromagnetic part of the difference is. If you measure the gluon radius of this proton, the gluonic radius, and the quark radius, you will find an experimental result that says this is a Gedanken experiment, by the way, a thought experiment, that the gluon radius or the color radius will be larger than the charge or the quark radius. You would do charge by electron scattering, and you need something new to measure using gluon distribution. At some different energies, you have these constituent quark model, where the quark is surrounded very closely by the gluons like this, and you boost it and you can see that this is what it would look like. And in this situation, if you were able to measure the gluon and the quark radius separately, you will not find any difference. You'll always find that wherever there are quark, there is gluon, and normally the distributions are going to be very similar. And lattice gauge theory is telling us something else. It says that there are 3 points, like there are color charge points, and then there are the nodes, and then the gluons sit inside. They're binding them together like this. And if you perform an experiment, a Gedanken experiment in the future, and a real experiment in the future, you would find that the gluon radius on an average has to be smaller than the quark radius. The answer to this question is we don't know, because we've really never seen a proton in a transverse dimension, and protons separated for quarks and gluons. What we do at Jefferson Lab with the high intensity electron scattering, we do the electromagnetic part. We understand the electromagnetic radius. And what we normally call proton radius is the electromagnetic radius. And we want to see whether the gluons are confined in the same radius. It might be that the gluons are not confined in the same radius. It might be slightly different. And there is nothing that tells us it shouldn't happen, because we have seen that when a proton and a neutron sits inside the nucleus is bound by something called pion cloud. Where does the pion cloud come from outside of the proton and the neutron? It has to come up from some QCD phenomena, some way to create those quark-antiquark pairs that create the pions that make the cloud outside of the proton, but inside the nucleus. I believe that there is an origin of that has to have something to do with the gluonic charge not being confined to the same radius as the proton. But we don't know how to do that. So I mean, we have never seen this. So we would like to see that in the future experiment. Fortunately, a good formalism has been evolved in the last 15 years. There is something called Wigner distribution. The Wigner distribution is made up of this X Bjorkane, the transverse distance of the quark from the assumed center of the proton, and the transverse momentum of that quark with respect to the proton, the transverse momentum, transverse distance. If you integrate over the transverse momentum, what you get is an impact parameter distribution. And if you integrate over the impact parameter, you get your normal unpolarized Parton distribution function. On the left-hand side here, if you go integrate the BT, the distribution of position, what you get is the TMD, is the transverse momentum distribution. Some of you in the audience might be studying it. There are very strong groups in India that study this theoretically. But if you integrate over KT, then what you get is the regular Parton distribution function. If you take the Fourier transform of this impact parameter, what you get is something called the generalized Parton distribution function at a particular parameter, which I will describe a little later. I'm sorry, I should have described it early before this. But there is a parameter that says the skewness, that tells us that when the photon comes in inside the proton and interacts with the quark, it excites it, and then the quark gets de-excited. If the difference between the initial momentum and the final momentum is not the same, and especially when in a particular case where a virtual photon comes in and a real photon is created in such a collision, then the quark carries different momentum fraction before and after such emission. And that skewness is called this Z that is called here. The X and T are the same as normally what we see. But anyway, the whole formalism of how to get to a three-dimensional picture, a momentum times position picture of a parton now exists. About 10 years ago, it was not there very clear how to do that. And now we know how to measure all of that. And that's something that we will do. I want to remind you of the same picture that I showed you before. Before, you probably could figure it out at this phase because you had an idea about how Statue of Liberty looks. And that's why you were close to it. Your mind was prepared for it. Now let me ask you, if you don't know anything about the three-dimensional picture of the proton inside, then it is very difficult to guess. And I claim that this is going to be more difficult to guess. This is another painting, a very famous painting, and I'm going to go through very quickly to make the case that if you don't know insights of something, if you don't know what the painting is about, if you have no idea about it, no intuition about it, which is the case for us in terms of QCD inside the proton, it is rather difficult to judge. This is a very interesting and a very strange painting by Salvador Dalí called The Persistence of Memory. So what I wanted to emphasize here is that it's a weird painting, nothing unusual about it. Well, QCD is weird in a sense. It does make you off base compared to QED in terms of interactions. And that's why you cannot really extrapolate QCD as simply as we extrapolate QED. Instead, we have to actually make very precise measurements of everything that goes on. We know how to make those measurements. We do simple transversely polarized proton electron scattering. And when the quark, we have to think about the quark moving in a circle because the quarks cannot leave the proton. They have to turn around when they can't be stationary. So when they come to the edge of the proton, they have to turn around. That would anticipate creating a transverse motion and a transverse orbital motion, possibly. If I hit the quark in that orbital motion, I will see a left-right asymmetry in pions and kaons produced depending upon which quark I hit. And from there, after doing enough simulations, we will then come to a picture that looks something like this, a large set of events that will make this plot. I've told you that that's the momentum picture. I want to see the position picture as well. And the position is a little bit more difficult. The position and momentum inside, if there is actual motion of partons inside the proton, and if I want to actually sense it, there is no point in killing the proton, meaning destroying the proton. I want to go inside the proton very, very gently. That means I want to do a deep dive inside the proton. So the deep inelastic part should exist, but it cannot be as violent that it will break the proton, because if it breaks the proton, then the motion that I'm looking for, the orbital motion of the quarks and the position and the momentum correlations will be lost. So I want to do a non-violent collision. And what better can one expect to explain that by going to the non-violent movements that these two gentlemen pioneered, one in India and one in the United States. So this is the deeply virtual Compton scattering, which I call the non-violent collision. What is happening here is like the electron comes through, emits this photon, a virtual photon, and that photon interacts with the quark inside the proton. That then gets excited and gets de-excited by releasing the real photon, and this thing comes back. So there is a real scattering angle between the initial state proton and the final state proton, but the proton remains intact and a real photon is created. If the interaction happened in the next to leading order way, and a gluon comes through, a quark-antiquark is formed, then it interacts with the photon, then it forms a vector meson, and the gluon falls back without breaking the proton. These are called deeply virtual Compton scattering and deeply virtual vector meson scattering. And this is where that C article variable that I used before comes through. The transverse momentum between P and P prime, the initial and final, if you take the Fourier transform of that, that starts giving you the spatial distribution of the partons that you are exploring. In this case, the gluons, and in this case, the deeply virtual Compton scattering. In this case, just the cross-section of it and the evolution of it cross-section starts giving you the gluons distribution inside the proton. So both combined, you'll start giving you not only the momentum from the transverse momentum distributions to semi-inclusive DIS, comprehensively with this process starts giving you idea about the full picture, a three-dimensional object as the proton should be. And for that, you need to measure the scattered proton or the scattered nucleus if we are making this measurement with that. So both together will allow us to make measurements of the transverse momentum and transverse position of the C quarks and the glue, whether they are polarized or unpolarized, etc., etc. These are polarized quark simulations for momentum These are polarized and unpolarized quark distributions and C quark distributions for position. And together, as you can see, if you know the momentum and the position, you start building the orbital angular momentum. And that's the beauty of this future collider. The lattice QCD folks have started calculating these things on the lattice, and that's an amazing thing that you can calculate things that we can now compare with the future electron-ion collider. And I believe that this kind of a measurement will be absolutely essential to understand the deep aspects of the transverse momentum distributions of the quarks inside the proton. In shortness of time, let me go, I have to do one more thing. Here is a distribution that we might get of the gluons as a function of BT, the transverse distance. I told you that you want to make measurements of the transverse picture of the proton. I want to see where the gluon distribution ends. I already know where the quark distributions end. I want to see where they end. And you can see that the simulations tell us that we can get a very high resolution picture of the gluon distribution at different values of center of mass energy, running the collider at different energies at a function of x. This is the x vector meson. It's close to the x Bjorkane, but not exactly the same. But the idea is the same. You're making measurements with different values of the momentum carried by the vector mesonic quark systems. The interaction region that you need to make such measurements is extremely important. We have never tried to do this in the past. And on the right-hand side, the picture tells you that this is the same curve as one of them curve. But if you don't accept the final state proton that I mentioned to you before to make the P prime measurement very well, if you miss the low momentum side, remember this is the range of 0.03 to 1.6. If you miss the low momentum side, suddenly your uncertainties blow up like that. If you measure the high momentum, if you miss the high momentum side, you instead of 1.6 GeV squared, you make 0.65 GeV, then suddenly you start getting uncertainties in the low side. So while designing the experiment to which I'm now coming, we need to be very mindful of such things that will be very, very critical. So what I'm trying to do is I'm going to make a three-dimensional picture, a non-violent electron watermelon picture by making an MRI of the watermelon inside. So want to make the three-dimensional picture. Suppose there was an inherent motion of particles, of things inside the watermelon. Suppose the watermelon was alive. You wouldn't want to cut it like the way the center person is doing. You want to study its orbital motion of things inside. And so this is what we want to do simply. Last but not the least, I told you that this process of gluon splitting is very important at high energy processes. In the Nobel lecture of Frank Wilczek, Origin of Mass, he talks about this. He says that such a gluon splitting is very natural and a result, but he also talks about that this will continue. This will keep on going, and a small color charge here can result in a huge color thundercloud, and essentially he stops it at that point. And the physicist in us asked, so is this infinity? Is this going to infinity? Of course not. Now, he was talking about a color charge in isolation. Well, there is no color charge in isolation. You really cannot have that in reality. So what can we have? In reality, this whole thing sits inside a proton or a nucleus, so it's confined. If it is confined, these things cannot leave the confinement, the volume of the proton. And that means that at some point they start becoming extremely crowded. And now these two gluons can now merge into a single gluon. Those gluons can merge into even smaller and smaller, etc., etc. But at some point, the growth and the reduction will become equal, and this saturation regime will occur. And that's what we are calling the saturation state of gluons, or color glass condensate, which is one of the discoveries that we would like to see. The gluon rise is seen from Hera. This is the Hera plot of gluon distribution. These are the other quark distributions coming from the global analysis. What we have not seen is the turnaround, or like the saturation of this. And that's something that we want to measure using a nucleus. Instead of a proton here, we want to use a nucleus and explore a large number of partons simultaneously to see if we can get the saturation and oomph factor of a to the power 1/3 divided by x. And that saturation scale that we are looking at Hera at 300 GeV with the electron proton was sitting somewhere between 0.035 to about 0.5. So this is the range where we have explored where these gluons come from. But at the EIC, because we are replacing the proton with a nucleus, even with 40 GeV E gold nucleus will be sitting somewhere here, and a 90 GeV E gold will sit all the way here. So we think that we can discover, if we are lucky enough, we can discover a very, very brand new aspect of the QCD matter, a purely gluonic form of matter in cold state. And that would be a fascinating thing to measure. And the way to measure that, it has properties which are unusual, I told you, like a brick wall, and it's a solid steel wall, 100 times more more dense than the neutron star estimated. So what will happen is, if you see two jets produced in EP or EA collisions, then they will be either very, very distorted, or ideally they will be missing in the EA part in the saturation region, where the electron proton will be a clean, simple measurement. And that is shown here by the suppression that will be seen. Let me, in the interest of time, this is the summary of the science. I want to quickly go, if I have another 10 minutes, 5 minutes to explore what the realization plans are. So here is the summary of all the physics that we want to do. And this connects to the luminosity versus the center of mass energy of the machine that we want to build. Around 50 GeV at this luminosity, we can do the nuclear science that we all mentioned there. And with the spin, we would need 10 to the power 33 or 10 inverse femtobarns to make measurements of that kind. To see the tomography, we want to get to a much higher luminosity and possibly a wide range in energy to see the scaling violations of that, and you would get these pictures. And for the study of saturation, we want to go to highest possible nuclear energy or collision energy. You can also do some measurements at higher luminosity, but it doesn't seem to be necessary. If we are lucky, we'll see it very quickly using some of the probes that I mentioned to you before. The new directions in science are always launched by tools, new tools, more than new concepts or new ideas. I mean, there are very, very few ideas that came first, and then physics was built upon it. Every idea has to be based on nature, and it's a very natural thing to do. It's an experimentally driven science. Unfortunately, in undergraduate sciences, anywhere around the world, we have a very distorted view of physics. We do a lot of theory first. 80%, 90% of our classes are theory, 10% are experiment. Actually, the theory that we study has come from the experiment. So it needs to be approached that way. And this is embodied very nicely by Freeman Dyson's idea and concept. And that's what we want to do. So the design of the Electron-Ion Collider, we want to build it inside the RIG tunnel. And what we have is the blue and the yellow beams. They already exist. We'll only use the yellow part of it. And the blue beam will be the injection for the electron, a different type of machine, not the same magnets. And the electron will be injected from the 2 o'clock region here. It will circulate through the RIG. It will be injected into the accelerator ring, and then electron ring will collide with the yellow beam in the IP6 and hopefully also in the IP8 region. There is a beautiful physics of cooling of the electron beams, of the nuclear beams, that I will not be able to talk about right now, but if there are questions, I can address them certainly. And the luminosity performance is going to be this is the same physics plot that I just showed you, and the luminosity performance of the machine is expected to be something like that. So it will allow us to do all center of mass energies over a wide range in luminosity, and extremely high for that one. This is what the complex might look like. The proposed detector area, this is the location of the star detector. Many of you might be part of that. And then this is the part of the Phoenix detector. Some of you might be part of that. I was part of that in the past. It's a very unique machine. These are all the experiments done with electron-ion collisions of the past. And you can see that, that as soon as you start saying a wide range in luminosity and wide range in center of mass energy, most of these experiments fall off. And then when you say we want polarized protons and nuclear beams, then there is really nothing in the world which is being even proposed in the next 50 years. So it's very, very unique QCD facility. It will go to where no man or woman has gone before. Well, how does that work? This is the X and Q squared plot. And these are the past experiments. These are some of the current collider experiments. The electron-ion collider in both these cases will explore extremely new areas in the dynamics of the proton in X and Q squared space. And similarly, in the nuclei, it will go to regions where no past experiments could go because they have never been done in the nuclear environment. It's a new tool. It needs new detectors. And the concept detector is this. You have a detector, you have electron beam and the ion beam. The angle between them is between 25 to 35 milliradian. The shown here is the exaggerated the angle, of course. What we normally do in collider detectors is that we see everything that comes out in the central part of the detector, which is shown by this cylinder. We want to measure them extremely well with particle identification, high resolution in momentum, as well as calorimetry and hadronic calorimetry. However, in addition to that, we want to measure what happens to the electron once it gets scattered. So we need to have very forward, very backward electron going direction detectors. And also, most importantly, I want to study the entire nuclear fragment that happens. So after the nucleus breaks, I just don't want to fit myself inside the central detector, but also measure everything exclusively what happens to the very forward part. So that is the challenge. We really want to get to as close as 100% as possible to do that. And that's what we try to do in this yellow report, which was produced over 2 years of studies. Many of you were involved in this, 902 pages of publication that come up with a detector design. And this is the approximately what it looks like, the ideal detector with a silicon tracker, a TPC, particle ID, EM-Cal, magnet, and hadronic calorimetry. And in the backward electron direction, the transition radiation detectors, particle identification, EM-Cal. On the right-hand side, where the hadrons are going, there's gaseous rich TRDs, EM-Cal, and H-Cal. Now, that's the ideal detector concept. The real detector might look somewhat different, but we would like to come as close as possible functionally to it. And a three-dimensional rendering of this is shown here. There are now proposals, the detector doesn't stop here. I remember I told you that I want to make measurements of the scattered proton very precisely to get as close as this possible of the color radius or color distribution. And here is the interaction region. Here is where the detector will sit. This is the whole central detector will sit here, but the forward and the backward detectors will extend all the way to 50 meters around the IR to make measurements of the remnants and the fragments as precisely as possible. It's a very unusual and a new concept. There are 4 concepts evolving currently. One is using the S-Phoenix detector. This is the central part of the S-Phoenix detector, which will be followed up by a forward and a backward end cap to make a first claim of the claim that it will be reusing everything and make measurements of that. Some of us, and in my Indian colleagues, which are many of you are in the corridor, the audience here, want to make a brand new detector for this called the Athena, a totally hermetic detector to do that, to build as close as possible to the detector that we just said in the yellow report. This is an early 3-dimensional rendering of it, and we think that is the best way to do it. There is an experimental effort called CORE, compact detector. The size of this detector is of the order of 1/3 of these 2 detectors in volume. The idea is to have high precision using modern technology, high resolution detectors, but try to reduce the volume, but to save the cost. So we'll see what that happens. So it's very similar in functionality as the claim by the proponents, but it will be looked at in the next few months and evaluated. And then there is some effort that is going on to make measurements at the low center of mass energy. So people are looking if any of these detectors or a new detector is needed only to focus on the very low center of mass energy part. There are some interesting physics that people claim they want to do with a dedicated detector that can be very specialized at this low center of mass energy. We don't know whether this will happen yet, but there are proposals which are coming up. And so there are these 4 websites that you can go to and see what the details are and explore what is going on. There is a large a user group community which is now standing up, about 1,300 of them from 230 institutions and about 34 countries. And I'm very happy to see a very large contingent from India in the Asian part. In fact, it is probably the biggest contingent, even after United States even in the big pie in terms of the number of institutions. So I'm very encouraged as what I can see as the Indian students and postdocs taking over very significant jobs in the future on the Electron-Ion Collider, and it will grow. So this is a new tool. I want to finish this talk because I give you a time scale. Here is where we are, about 21. We just got the CD1 in June. We are designing it still. We'll continue to design until about CD2, when the engineering designs will be ready. After that comes the phase of conventional construction. We'll start ordering things after the CD2, CD3A. That's what this means. Order things for the infrastructure, the detector, and then the construction starts around 2024 or 23. Continues until somewhere around 27, 29. This is the place where around this time might be the first collisions. For this, we need at least some detector components ready. And then eventually there will be an extension of the full detector ready somewhere around 2032 or 33. And this range is uncertain. That's why you can optimistically claim that you could have first collisions here and the first collisions for physics here. But this is a range that is given formally. In summary, thank you for your attention. The science of the gluons, the super-Gluon particles, is what is driving us. I hope I gave you a flavor of what that means. The US project has a significant momentum now. It's moving very quickly. First collisions are expected around 2030. It will be an exciting time, even if they are engineering collisions, meant to understand the proton, the machine itself. I believe that there will be good science to be done. And before that, there is going to be a huge amount of a learning curve for building these detectors. So it's an ideal time for students and postdocs to get involved and really join this effort where you will get hands-on experience building new detectors, which is something that unusually happens, because as you have probably seen, that every 7 to 10 years, there is upgrade of the detector at LHC or RIC. And you get, if you're lucky, you're in that time, you can contribute to detector building and then continuing on the physics. You happen to be, the people in this audience happen to be in that lucky form where a full detector, not just an upgrade of a detector system, a full detector, and maybe 2 detectors will be built in the next 10 years. And I hope that we all push our students, postdocs, young faculty to take significant responsibility so that we can generate the next generation of the scientists that will be needed going beyond even the EIC and come in with new ideas of new detector technologies. So thank you very much.
Okay, thanks a lot, Professor Deshpande, for this very, very interesting talk. And now we are open for questions. So you can raise your hand or you can directly unmute and speak. Yeah, so,
yes.
Yeah, please.
Go ahead, Swapnish.
Yeah, hello. Thank you very much for lecture. Actually, I have a question regarding HERA and EIC. So I got the point that EIC will be very high precision measurements and over wide energy variabilities. And apart from that, what are the other advantages of EIC over HERA that I want to see?
So HERA was a 300 GeV center of mass energy machine, right?
Yeah.
We have about 140 GeV at the most. Now, practically, just to give you a picture, the luminosity of HERA was 10 to the power 29 to 30. And we are aiming for 31 to 33. It's about 100 to 1,000 times more luminosity. Second difference is that HERA never had nuclei. We tried to, I was actually one of the proponents of it. And I was also proposing to polarize HERA in 1996, 97. And both were turned down. And we had asked for $35 million to do the science that we want to do with the Electron-Ion Collider at that time. And we could have done it using the Zeus and H1 detector. If we had polarized proton beams, which they did not, so the Siberian snake magnets that Rick now has and EIC will have will not be there. And nuclei, the change in the nucleus was not there, right? So those are the practical things. However, I want to say a little bit about the physics of it. People think energy is the only thing. You want to increase the energy, you want to go to the higher energy. By increasing the energy, you're looking at smaller distances. Remember, what we want to study in QCD is the collective behavior of these partons inside the proton or in the nucleus. To do that, I don't need high energy, but I do need to take many snapshots of the way the proton behaves as a function of time. So I need high luminosity, not necessarily high energy. You see my point?
Yes, sir.
And then when you start seeing that collective behavior in terms of the spin orientation, where does the spin of the proton come from? Then I need polarization of the beams. I don't need high energy, right? So that's the main difference. So I want to, and this is where the P and the lambda comes from, the resolution. I don't want to increase the resolution to such a level that I'm looking at substructure of the quark. I mean, that's interesting by itself, but LHC will do that in proton-proton collision to look for physics beyond the standard model as we know it today, right? They will see if a quark is splittable. They will see if quark can interact and electron can interact with each other and form a leptoquark. Those are physics beyond the standard model. Those are distance scales which are extremely small, but it doesn't help me if I'm more interested in the collective behavior of the QCD. Yeah, emergent behavior is what I'm looking for. So I want to actually go away from that. I want to increase the distance of my scale, look at larger lambdas, but not large enough to go outside the proton. Yeah, that's why those are the differences between HERA and LHC and EIC.
Okay, thank you, sir.
Hello.
Hi.
Can I ask you a question?
Sure.
Yeah. First of all, thank you. This was a very interesting talk and I have learned so many things. In one of the slides there was a question that can we study a new state of matter using EIC? Which new state you were referring to? Was it the gluon saturation?
That is correct. That is correct. Yes, absolutely. See, the prediction, if all the theory is telling us is right, it would be a essentially gluon dominated state of matter. Remember, heavy ion physicists are very used to saying phase of matter. This is not a phase of matter. This is not a transition happening from quarks and gluons into, they are combining somehow differently. No. I'm going to a regime in which quarks are completely rare. They're only dominated by gluons. That is shown by that HERA plot of gluon going up. So the fraction of quarks is extremely small. And what remains in that region, in the very low X region, is only C quarks, which are coming out of the glue and going back into the glue. So it is a gluon dominated region. And that's the state of matter that we want to study. So they call it a state of matter. It's a very subtle difference, but it's important. So phases can change from one to the other. States cannot. So that means that it's telling us that in every proton that is at high energy, or if you look at the proton with high energy probe, you should find it in you and me. That's what it's telling us. Yeah? Did I clarify that, Meenakshi?
Yes, absolutely. Thank you.
Yeah.
Do we have more questions?
Siddharth, can I
Yes, Tapanda.
interject?
Hey, Tapan, how are you?
Yeah, hi, Abhay. Very nice talk. Really enjoyed. Nice to see you. So I have a very small question which is already asked before. Would there be any advantage going towards fixed target also in addition to the collider mode? You see any kinematic advantage in any physics you discussed?
Yeah, so the collider is normally promoted as a machine for low X physics because it gives you the extra S, the square of the center of mass energy.
Yeah.
And then so very naturally you can go to lower X. If you really want to provide, you go to the highest possible X, then most often you go to a very intense fixed target experiment. So that's typically what it is, the situation. However, there are geometries even in the collider that allow us to do high X measurements, but the cross sections fall off very rapidly. And because the fixed target experiments typically are done with solid state targets, you have a natural advantage of 10 to the power 39 or 38 in luminosity compared to the 34 that a best collider can give. So if in addition to the 34 and 38 difference, if you have nature telling us that the cross section is going to fall as you go to high X, then you are at a very significant disadvantage. So then that is the sort of holding us back. But the geometries exist. There is no reason why a collider cannot make measurements of the high X region. The geometries exist. In fact, the highest measurement that I did with my student at Zeus was 0.9 in X, which is unheard of, right? You can look for a geometry, unusual geometry, but we found something like 100 events over the 10 years of operation, right? It's a beautiful, cute way of demonstrating something. To extract physics from it is very difficult. It's very difficult to compete with fixed target experiment if you really want to do that. The second thing that is missing, in my opinion, is that the advantage. I mean, there are still some advantages. You see the nucleus collision that I've talked about. And let me just show you the plot again. Am I still sharing? I guess not. Oh, I'm sharing.
No, you're not.
Let me go to my plot if I can. Remember the electron scattering of a nucleus, which I had a cartoon at the beginning. Yeah, here. This plot, this on the left-hand side that you see.
We don't see it.
You don't see it.
No.
Okay. I wonder why. Okay, let me just see why. Okay. What are you seeing?
We see you. Very nice.
Okay, let me just take this out. I don't know what happened to that screen. Okay, how about this now?
Not yet. Your slides are in Indico. I can just.
No, not yet, but I will do that again. Let me share it again. 1 minute. I stopped sharing, I think.
Yep.
Okay, and I wanted to show you this plot. Which one is this? This plot. Okay, so what happens in so this one, the left-hand side, now you can see, right?
Yeah.
Yeah, okay. So in the fixed target experiment, if you perform such an experiment, it's very difficult, if not impossible, to make measurements, precise measurements of what happens in the target fragmentation right here. Because you're sitting inside a solid state target. So when you scatter electron off of a nucleus, you can see the scattered nucleus electron. So you know what happened inside, the kinematics of what happened, but you don't know what happened inside the nucleus or what happened outside the nucleus here. You have no control because outside this nucleus is another nucleus atom, and this is going to hit first the other atom. So it doesn't reach your detector very well. In the nuclear collisions which happen in the collider, it's not a solid state target, but rather it is a gas of nuclei in a bunch, which means that once the nucleus is being hit, then the remnant as well as the scattered part, the jet as well as it actually emerges. Even if it is low energy, it emerges outside. You just have to be very, very, very innovative in catching it. So in the fixed target experiment that were done in the past, it was very, very difficult to study the nuclear fragments of the electron nucleus collision, because of which we couldn't understand quite a lot of interactions that happened inside the nucleus. And that's a big difference that a nucleus will do. So that's an advantage of a collider over a fixed target experiment. So although
that's the nice way to put it. The second part. Yeah.
The second part,
Yeah.
because you lose otherwise in luminosity. In the proton, you can never win. But in the nucleus, we have never seen such a thing, right? All the experiments in the past with muon scattering or electron scattering, they couldn't see this because it was very difficult. And we know from COMPASS experiment at CERN, when they went for semi-inclusive inelastic scattering measurement, they had to make a very concerted effort to do that. And still, they have very limited acceptance just because of the fixed targetness of it. So whereas I think the nucleus in the collision for collider, it has more versatility.
Thank you so much. I think I really got a very nice idea. This was a really good thing for the students also, starting from the beginning of the nucleus to atom to EIC all the way. Thank you.
Professor Abhay, may I ask a question? So
yes, sure.
Yes, actually, I do not know whether it is relevant at all, or I do not know, it is a stupid question. So nowadays, after this onset of LSC, we are seeing a lot of effects in proton-proton collisions, which are basically puzzling us both in the experimental and theoretical in both fronts. And one explanation, people are trying to understand it in terms of something is formed like in heavy ion and a medium is created, and that is basically responsible for all those effects. But the other group, they are basically trying to understand it in terms of the geometry of the proton or the distribution of partons inside the proton at this energy, which is basically root S is 13 TeV. So those will also means kind of put some light on this kind of thing also to understand.
That's a wonderful question. That's an absolutely great question. I remember the day on which I think, and I think the heavy ion, Tapan and the heavy ion folks can correct me, the day on which CMS published their result on Ridge. I think it was 2012, right? Or something like that? Or maybe
yes, 2012. Yeah.
2012. That was a transformative day for me personally. I'm not a heavy ion physicist. I came from spin, but I have grown to understand that there is really no difference. QCD is QCD. Whether you do this with proton-proton scattering, proton-antiproton scattering, nucleus-nucleus scattering, electron-nucleus scattering, the physics of QCD is universal. And that has to be universal. And we are the ones who are not seeing it. You know, in our background, there is this wonderful story about an elephant comes to a village of the blind. And every blind person is curious to know what the elephant looks like. And whoever touches the trunk says, oh, the elephant is like a big thick rope. The elephant, you know, you get the point, right? You remember this story from our, when we grow up. And we are doing the same thing to QCD right now. We are measuring things about QCD in different angles with different tools, and all of that is important. So when I saw that result from CMS, I remember that day, that morning, like a clear morning. I remember it. I sat down, I printed that paper out, and I said, I don't want to do anything today. I want to understand this. And the reason why I thought it was done was because this question that we ask here at the bottom of this question, what happens to the gluon density in nuclei? I could simply put it as a proton. I put it as the nucleon because I know that at 300 GeV, Hera has already explored to see if there is saturation of this kind, collective behavior. You don't even have to call it saturation. This collective behavior of gluons, when you push lots and lots of gluons together in a volume, how do they behave? That question at high energy is coming. And I had a very long discussion. I remember when I was a postdoc as a Riken fellow at the Riken Center. T.D. Lee and I used to have these discussions once in the afternoons. And he has a paper. He showed me that paper. He said, the protons and nuclei at highest energy should not be different. They should look exactly the same. And I claim that the gluon inside a proton at 14 TeV and a gluon inside a nucleus at equivalent, I don't know, 2.7 TeV should not know whether they're part of a nucleus or a proton, because around them, they see a huge crowd of gluons and quarks, or gluons at the high energy. So the collective behavior that you are seeing now at LHC is absolutely connected to the collective behavior that every one of us is looking for. The question is that using proton-proton or nucleus-nucleus collisions, you always will have 1, 2, 3 different explanations for it. Yeah, those explanations cannot be resolved cleanly because both the two colliding particles, the proton on proton or nucleus on nucleus, they both serve as probes of the other, and they're both very complicated. In the electron nucleus or the electron-proton collision, I'm taking away the structure of one of them. And now what is left is only the target, which has the complicated QCD in it. The electron doesn't have it. And I'm going one more step forward and using the electroweak force exchange between the electron and the nucleus to explore what's going on in QCD. Yeah. So I actually believe what you just said is absolutely important. So what you're measuring, what you're seeing as the spatial effects, they have to be the TMDs, that the transverse momentum that comes naturally because of those TMDs that you have to believe in the PP collisions. I've seen the W production cross-section from LHC, both CMS and Atlas. And I know that unless they tweak the generator with input of the TMD that we measure in our fixed target experiments at Jefferson Lab, you cannot get the best match of the evolved Parton distribution function that comes off your W physics at the highest energy at LHC. The same thing, I believe, is happening with the position. So your question is extremely clear, extremely pointing. And I think most students, all of these students in this audience should remember this question. It is a very important question. And I believe that we will all eventually solve this by looking at it from different angles. Position is important, momentum is important. We were ignoring both of those in the past experiments. Why? Because a great man like Feynman said that you don't need them because that's a very small dimension. Most of the momentum is in the air, in the collision dimension, and you can do most of the physics using it. Yes, he was right. In 1950s, he was right. Now we have improved our tools and technology to such an extent that a 300 MeV deviation of a transverse momentum of a quark is now being seen in a W production plot of a proton at LHC, which is at 14 TeV. So your question was not foolish, nothing fundamental. It's a very fundamental and a most basic question, and it should be very natural. I really like that. Very good.
Okay, thank you. Hello, sir. May I ask one question?
Yeah.
Hello, yeah. My question is, in Alice energy, people are searching like exotic resonances, like blue balls, candidates, and composite objects of tetraquarks to understand the properties of particle production by indirectly information of gluon properties. Whatever your comment on EIC, that we can, that property, even though you talk about the spin property, we can understand the spin component. That information we also can get from looking.
You mean exploration of multi-quark systems and
like the global candidates like Hira measured like electron proton collisions. They measure like global candidates the global candidates, they propose there is no valency quarks. It is composed of only gluons. So
Yes.
that indirectly tells the properties of gluons have dominated. At the LHC energy, we know as increasing the energy, the gluons are dominated on the particle productions. So due to the high energy and also the high statistics available, so people are looking this exactly resonances like glue balls to understand indirectly the properties of the dominant of gluons
Yes.
property.
So the same tools and techniques that were used at HERA will and can be used at the EIC to study the same thing. You would have high luminosity, high number of events. If they exist in the higher, somewhat higher X region compared to the HERA that you could explore, you would do the same physics. For multi-quark systems, yes, the same thing. Tetraquarks, pentaquark searches are happening now. I mean, the studies of that is just starting. So if you're interested in that, I think there is a group from University of William and Mary, led by Justin Stevens, and my new postdoc, who is Bill Lee. They are the experts at these kind of searches. So if you're interested, send me an email, and I can put you in touch with them, and I would be very happy to see this sort of physics grow. I haven't seen that because we didn't think it was, I see, when you make a case for a collider, so far we are in that phase in the last 20 years, you always look for physics that is so unique that nobody else can do, because that's the way to make the case. But once it is approved, now we are exploring what else can it do, and is it comparable to the other studies. So this falls very clearly in that. So the Hall D at Jefferson Lab, which does this routinely, exotic QCD studies, people from there, and I know that LHCb folks are now getting involved with the EIC to study this. I did not know that Alice had such a search, but I'm not surprised. But if you are interested in that, we just need to explore it. I don't know that people have looked into and it seriously. In fact, this would be an opportunity for you to take lead in that. So I highly encourage you. So send me an email if you're interested, and if you have time. Then we have.
Because my question is because these resonances still not, we don't know the like structure and properties, either what is the spin content and what is the composition. It is also related to some fundamental properties still we do not know and need to be explored. Okay.
Yes.
Okay, thank you. Yes.
Yeah. I think this is important, and I think it is the exclusive nature of detector acceptance will always help such searches. And using fundamental known laws of physics about spin conservation, et cetera, if you have full acceptance, I think it will be a very exciting program to do at the Electron-Ion Collider. We just have not done it, but I highly encourage you to get involved. I think that would be great.
Thank you, sir. Do we have more questions? Okay, looks like not. So then I think we thank Professor Deshpande once again for this nice talk. We had some interesting discussion. And
okay, thank you very much for inviting me. It was a pleasure. And the questions were excellent, I must say. And I hope to communicate with you more often, with all of you, if you can.
Okay, thanks a lot for joining.
Bye-bye.